everyone. Welcome into lecture number 7 of linear algebra. This lecture we're going to discuss linear independence. And let's get started with a couple of theorems that are going to motivate the rest of our discussion in this lecture. So we'll just call these Theorem 1 and Theorem 2. We'll start with Theorem 1. So Theorem 1 says the following. If we have n vectors, so v1, v2 to vn in a generic vector space V, so here let's write this down, where V is a vector space. This could be any kind of vector space. It's just got to obey those 10 axioms that we discussed earlier in the semester. So if these n vectors live in this vector space V, and suppose that one of these is a linear combination of the others. So here let's suppose that, let's say Vi is a linear combination of the other n minus 1. Remember, a linear combination means that it can be written as a sum or difference of scalar multiples of the other ones. Linear combination, we'll call this LC for the rest of the lecture, but if it's a linear combination of the n minus 1 other vectors, then the result here is that the other n minus 1 vectors span the same space as the first n. So then here's the deal. It's kind of, the way I've written this is a little crazy, but the span of the whole group of them, so v1, v2 through vn, is equal to the span of the ones with this one removed. So the span of v1, v2, vi minus 1, vi plus 1 through vn. It could be n is the last one, but so the idea here is that we've taken out, right? We've deleted the ith one. But the whole point here is that they span the same space. So these are going to span the same space. So let's look at a proof of this. So let's prove it. So first of all, let's suppose without loss of generality. So this is something that we say frequently in math when we're writing proofs, but without loss of generality. That means that we can make some assumptions to help us write down the proof that are not going to change the result of the proof. And to abbreviate this, we usually just write WLOG, without loss of generality. Let's suppose that the span of the vector space is the vector space V. So let's suppose span of these vectors V1 through Vn is equal to V. All right, because remember, a span is always a vector space itself. So the span of vectors in a vector space, it's always at least a subspace of V. So let's just consider that to be its own vector space, V. And let's also suppose that Vn is the last one is the one that's the linear combination. So, and further, that V sub n is a linear combination of the previous n minus 1. So we'll just write of the others. All right, so what we'd like to do is show that the span of the n minus 1 of those without Vn, right, without the last one, is still equal to the space V. So here's what we have to do. Because this is a linear combination of the others, then we can write this, right, that Vn is equal to, let's say, alpha 1 V1 plus alpha 2 V2 plus all the way up to alpha n minus 1 Vn minus 1. So by definition of linear combination, V sub n can be written as a sum of these other n minus 1. And of course, remember that this means, right, that the alpha I are all, for us, real numbers. They're elements, they're scalars, right? They're scalars. So for us, those are going to be real numbers. And then what we'd like to do is show that the n minus 1, these n minus 1 still span the whole space V, right? So let's suppose then that this vector V is a vector in uppercase V. And because we've said that uppercase V is defined to be the span of all of these, then we can write this V as a linear combination of all of these, including V sub n, right? So then V is going to be equal to beta 1 V1 plus beta 2 V2. So this is because it's defined to be in a span, right? this is going to be all the way up to beta n minus 1 Vn minus 1 plus beta n Vn. All right, and this is again, all these beta I are scalars. And this is true because V is said to be in the span, right? Because of the span. The definition of a span is that the span is the collection of all linear combinations of these elements. And so this is true because, or since V is in the span of V1 to Vn. All right, now all we need to do is kind of combine these two ideas here. So we've got this description of Vn as a linear combination of the previous n minus 1. And then we've got this description of V as a linear combination of the first n minus 1 plus a constant times the last one. So you can probably guess what we're going to do. Let me color code this a little differently, right? We're going to take this expression and just plug it into here. And then we'll be able to group this and write this as a linear combination of all of these, right? So we can write this out now. We can write the following. Therefore, our V is going to be equal to, so beta 1 V1 plus beta 2 V2 plus all the way up through beta n minus 1 V sub n minus 1 plus beta n times, and then we get our alphas involved. So alpha 1 V1 plus all the way through alpha n minus 1 Vn minus 1. And then we can distribute and combine like terms here, right? So these will all get distributed out and grouped together. So that term I didn't write down, but that'll get grouped together. This is just some algebra now, right? And so what we end up with then is that our V is going to be equal to beta 1 plus beta n times alpha 1 times V1. So that's a constant times the vector V1. Plus the next term is going to be beta 2 plus beta n alpha 2 times V2. And then all the way up through, this last one's going to be beta n minus 1 plus beta n alpha n minus 1 all times V n minus 1. And these are all real numbers, right? And so therefore, our vector V, which came from the span of the space with all n vectors to start with, is actually a linear combination of only these n minus 1, right? And so that's our conclusion, right? So therefore, this generic vector V is actually in the span of V1 through Vn minus 1. And that's what we wanted to prove, okay? So if one of the vectors is a linear combination of the others, then it's not needed in the span. If it's already a linear combination of the other ones, it's not needed. It's not necessary in the span. All right, and so there we go. We've proved that theorem. All right, so the idea, again, there, if we just try to put it into like heuristic language a little bit, the idea is we have the vectors that form a span, right? If any of them are linear combinations of the others, then they are unnecessary to the span. They might be, they might be desirable for another reason, but they're unnecessary to the span itself. And in our proof, we were able to show that if we kind of organize it a little bit more than the way I stated the theorem, but if we organize it a little bit better, then if the last one is a linear combination of the previous n minus 1, then you can just delete it and the span does not change, right? But notice that the coefficients become, in some sense, more complicated, but that's okay. The point, though, is that if a vector in a set is a linear combination of the others, then it does not contribute to the span in that sense, right? Okay, here's theorem number 2. So theorem 2, this one says the following. Given our n vectors again, so let's say we're given vectors v1, v2 through vn in a vector space V. It's possible to write one as a linear combination of the others. So this is now a question of when is it possible to do what we just did, right? So here's the answer. So it is possible to write one of these as a linear combination of the others. if and only if there exist scalars that satisfy the following properties. So there exist scalars. There's going to be n scalars now. C1, C2 through Cn, not all of which are 0. This is a key to the statement here. You'll see why in a minute. But not all 0, such that the following is true. That C1 V1 plus C2 V2 plus all the way up through Cn Vn if this is equal to 0. The 0 vector. All right, so if we can find constants that are not all 0, so you can always find, you can always say, right, put these constants equal to just 0, and then this will add up to the 0 vector. So the point here is that if we can find non-zero constants for which this linear combination on the left is equal to the 0 vector on the right, then that means that at least one of these vectors in our list is can be written as a linear combination of the others. All right, so again, let's look at the proof of this one. We'll maybe just sketch this proof. But let's suppose in this case that V sub n is the linear combination. So let's do the case where we suppose that one is a linear combination of the others and show that we'll get these non-zero constants, right? So here's what we'll do. Suppose in this case, again, without loss of generality, again, I won't say it again, but suppose that V sub n is a linear combination of V1 through Vn minus 1. All right, then just like we did before, we can write our V sub n is equal to alpha 1 V1 plus alpha 2 V2 plus all the way up through alpha n minus 1 Vn minus 1. And just by rearranging, if we subtract over this term, this is 1 times V sub n, right? If we subtract this one over to the other side, then look what we can write. So another way to write this is or alpha 1 V1 plus alpha 2 V2 plus all the way up through alpha n minus 1 V sub n minus 1 plus negative 1 V sub n equals 0 vector. All right, and so in this case we'll just put, this is almost what we want, right? We want to make sure that we have a linear combination where not all the coefficients are 0, and look at that, C sub n is going to be equal to a non-zero constant, right? So in this case we would just say, all right, we can put C sub 1 equal to alpha 1, C sub 2 equal to alpha 2, etc. C sub n equal to alpha n, C sub n minus 1, sorry, equal to alpha n minus 1. But here's the key, this is the one that's these could still, some of these could be 0, maybe all of these are 0. But the one that's definitely not 0 is this, right? C sub n is equal to negative 1, which is not 0. And therefore, we've got that direction, right? So we've got constants for which at least one of them is not 0, and the linear combination of those vectors is equal to the 0 vector, though. Okay? So that's one direction. The other direction is suppose that we have these such that, so the other direction then is to suppose that we have these constants, right, that are not all 0. Suppose there exist constants C1, C2, all the way up through Cn, not all 0. All right. So not all 0. For the sake of this, again, we can do our without loss of generality. Let's assume that V sub n is not 0, or sorry, C sub n is not 0. All right. But we want these, so this is more like a comma here. But these are going to now satisfy our property, right? That C1 V1 plus C2 V2 plus all the way up through Cn minus 1 Vn minus 1 plus Cn Vn is equal to the 0 vector. All right, we want to show that in this case it's going to be V sub n can be written as a linear combination of the others. So what are we going to do? We're just going to kind of undo what we did up here, do everything backwards, right? So the first thing we can do is add this over. Remember, C sub n is not 0, so we can add or subtract this to the other side. And we'll have then negative C sub n V sub n is equal to this linear combination on this side, C1 V sub 1 plus C2 V sub 2, all the way up through C n minus 1 V sub n minus 1. All right, and then we can divide through by this number again. Because we've assumed that C sub n is not 0, then we can divide through by negative C sub n, and we can write the following. So our V sub n is equal to negative C1 over Cn V sub 1 plus negative C2 over Cn V sub 2, all the way up through negative Cn minus 1 over C sub n V sub n minus 1. And so therefore, these are all constants, right? C sub n is not 0, so even if the numerators are 0, that's okay. Those are all constants, and therefore V sub n is a linear combination of the others. Again, without loss of generality. So V sub n is a linear combination of V1 through Vn minus 1. All right, and so that ends that proof. So these two theorems taken together say a couple of things. They say, number one, that, like we said, we already talked about this, right? But if a vector is a linear combination of the other vectors in a set, right, then it can be removed from the span without changing the span. So it's like extra information in some sense, superfluous. And then the other theorem is criteria for determining if a set of vectors has superfluous information. So if there is at least one vector in that set for which it is not necessary to the span, right, to creating the span of the space. All right, so these theorems together are motivation for the following definition. So we're going to use these two theorems as motivation to define the following item. So here's our definition. This says the following. So the vectors v1, v2 through vn in a vector space V, these are said to be linearly independent. So linearly independent, this is what we're defining, and it's exactly the situation of the previous theorem. So if and only if the following, if the following is true, that the linear combination C1 V1 plus C2 V2 plus etc. through Cn V sub n equals 0, if this implies that the coefficients must be 0, okay? So if the only way for this linear combination to be equal to the 0 vector is for the coefficients to all be 0. So the way we'll write it is that this implies that C1 equals C2 equals C3 all the way up through C sub n, that these are all equal to 0. And so that's the definition of linear independence, that the only way to make a linear combination of these n vectors add up to the 0 vector is for the coefficients to all be zeros. All right, so for the rest of this lecture, we have maybe one more theorem in our future, but for the rest of the lecture we have a lot of examples. So let's look at those examples now. All right, and let's see how this works. So our first example is the following. Well, we have a couple examples here, but here's a couple of pretty straightforward examples. First of all, in the two-dimensional space, these two vectors, 1, 1 and 1, 2, I claim that these are linearly independent. So how are we going to check these? By the way, if a set of vectors is not linearly independent, it's called linearly dependent, which is just obviously the negation of this. So how are we going to check it? Well, the criteria here says that we have a linear combination, C1 times the first vector plus C2 times the second vector, and it's supposed to add up to the 0 vector. And we know that in two-dimensional space, in two-dimensional real space, so these, by the way, these are in R2, right? So in R2, we know that the 0 vector is just the vector with 2 entries that are both equal to 0 here. So we want to try to solve this. This now becomes a system of equations with 2 unknowns, right? So the 2 unknowns are C1 and C2. And we want to show that the only solution to this is a homogeneous equation, right? The only solution to this equation is that the C1 and C2 must both be equal to 0. So for this example, we can multiply these out, right? If we multiply these out and combine this into a single system of equations, then it can be written as follows. So as a system of linear equations, look what we get. This then becomes the following system. So 1C1 plus 1C2. So C1 plus C2 is equal to 0. And similarly, the second row will become C1 plus 2C2 is equal to 0. And we've just studied a whole bunch of different ways to solve these kinds of systems of equations, right? So we could just do substitution and elimination straight from here, because this is just 2 equations, 2 unknowns. Almost the simplest possible situation, right? So we could do a substitution and solve for this way. Or we could use one of our matrix methods, augmented matrix, maybe a coefficient matrix with an inverse matrix, Gaussian elimination. We could do any one of those, right? But because this one is so straightforward, let's just solve this first equation. C1 is equal to minus C2. And then plug that into the second equation, right? So this one's then going to say minus C2 plus 2C2 is equal to 0. And of course, add that up on the left-hand side, we get C2 must be 0. But if C2 is 0, we go back up to this equation, that means C1 must be 0. And so just by a simple substitution method, we can see that both of these coefficients have to be 0. And so therefore, indeed, these two vectors are linearly independent in 2-dimensional space. Okay, here's a second example, which we'll keep as the same item here, but example number 2. Let's suppose that we have some vectors in R3 now. So let's say x is the vector 1, 2, 3 in R3, 3-dimensional space, right? And then I'm going to claim, so remember that we have these E1, E2, so, and then E3 is 0, 0, 1. I claim that these are linearly dependent now. So can we see this, right? Do we agree? Well, let's think about it. So x, E1, E2, and E3, again, I claim these are linearly dependent. All right, so I'm going to call linear dependence LD and linear independence LI, and then linear combination is LC as we move forward. I mean, I'll say the words, but I might shortcut how much I write here moving forward. But these are linearly dependent in R3. And remember, all we need to do if we think that they're linearly dependent is find non-zero coefficients that make this linear combination true, right? So that we can make these add up to the 0 vector. All right, so the easiest way to do this is to notice that actually x is a linear combination of E1, E2, and E3 to begin with, right? Because we can just notice that x is equal to 1e1 plus 2e2 plus 3e3. 1 in the first slot, 2 in the second slot, 3 in the third slot, right? And so therefore, look what we can do. We can just say, all right, e1 plus 2e2 plus 3e3 minus x. Well, that's got to be the 0 vector, right? Just rearrange this and solve. Move this to the other side, leaves a 0 vector on this side. And in this case, then, look what happens. C1 is 1. You're done at that point, right? But C2 is 2. C3 is 3. C4 is -1. The point here is that not even one of these is 0. All it takes is for one of these to be non-zero, and we have our answer, right? And so these vectors, since these are all not 0, these vectors are linearly dependent. Okay, so there's an example of independence and dependence, linear independence and linear dependence. So how can we determine if a system is, or if a set of vectors is linearly independent or not. This is the next item. So how can we determine this? Well, the answer is to solve a homogeneous system of equations. So this is good. We've just spent some time studying systems of equations, right? So solve a homogeneous system of equations. And we have some theorems about homogeneous systems from our previous studies of chapters 1 and 2. But first, let's make a note here. And what happened in the last example is actually going to always happen in general. So notice that in this space we had vectors, numerical vectors, right, in number spaces Rn. In this case it was R3. In R3 we had 4 vectors but only 3 entries, right? And so if we were to write out a system of equations, we didn't do it on this one because we just observed that we could find a linear combination very quickly and easily, right? But that was partially, it was so easy because E1, E2, and E3 are like the building block vectors. They're very easy to build linear combinations with. If these were more complicated and it wasn't obvious what the linear combination was going to be, we'd have to write out a system of equations, right? And just as we did on the previous example. And what would happen is that if we had 4 vectors, we'd have 4 unknowns for the coefficients, but we would only have 3 rows, right? 3 rows to make our equations. So we would end up with an underdetermined system with 3 equations and 4 unknowns, right? 3 equations and 4 unknowns. So in this case, when the system is underdetermined like that, then there's always going to be non-trivial solutions, and therefore whenever there are more vectors, right, than the number of entries in these numerical vector spaces like this, then we're always going to be able to say that these must be linearly dependent because they're going to form an underdetermined system which will always have non-trivial solutions. Okay, so let's see, let me write that down and then we'll see more closely how that works. But so if we are given more than n vectors, so let me write it as m greater than n vectors in a vector space Rn, then they must be linearly dependent. Okay, so what we really need to consider are the cases when we have exactly n or maybe fewer than n. All right, so let's look at one way that we could solve this. So here's an example that will help motivate how we can do this in the future. So let me first write down, let me finish my thought there. So what we'll do then is we will always use either an augmented matrix, or maybe we can even use our determinant since we're going to be solving a system of equations. And again, in the next example, I'll write out the system again, similar to the way we did it in the previous one. But if we have m equals n vectors in these number spaces, then we can use the determinant to help us because we have theorems about the determinant, which we'll review in a moment. And if we have less than n vectors, then we can use the augmented matrix approach. So we'll use augmented matrices. So here's an example where we are given, let's say, 3 vectors in R3. In this case, 1, 1, 1, 1, 1, 0, and 1, 0, 0. And the question is, are these linearly independent or linearly dependent? So independent or dependent? Well, like I said, what we can do is write down our system. So let's see how the system's going to compare to this, the way I've written this here, as a set of vertical vectors. So let's see. Our system is going to be C1 times the first vector. And the order doesn't matter, but they're given in this order. So let's stick with the same order that we were given. So C2 times the second vector, and then C3 times the third vector. This is all supposed to add up to the 0 vector, right? Remember our definition is that it adds up to the 0 vector, and then we have to solve for these unknown coefficients. And if we find that they only have the trivial solution, that C1 equals C2 equals C3, etc., equals 0, then we get linear independence. If we get any other solution, then we have dependence, right? So that's the idea. But the whole point here is that this is on the right-hand side is 0 vectors, so it's a homogeneous system. And then when we add this up to make our system of equations, this will turn out to be, the three equations will be C1 plus C2 across the top plus C3 equals 0. The second row will be C1 plus C2 plus 0 C3 equals 0. And then the third equation is just going to be C1 plus 0 equals 0. This one's easy to solve by back solving, right? It's kind of in a triangular form. But if we were going to write this as a matrix equation, look what it would be. It would be the first, right, column of the coefficient matrix is 1, 1, 1. The second column is 1, 1, 0. The third column is 1, 0, 0. The vector of unknowns is C1, C2, C3. And the right-hand side is 0, 0, 0. Okay? And so at this point, we have our matrix equation, and look how the vectors, the columns of the matrix equation, correspond to the vectors that we were given. They are exactly the same, right? And so it turns out that given our list of n vectors, so this is the case when we have 3 vectors in R3. When you're given the same number of vectors like this, you can just look at the coefficient matrix that you obtain by kind of dropping all the decorations here, right? So if this set of vectors was called X, then our matrix, we could call this matrix X, and we can just drop all these decorations, make this matrix. And remember that we had a theorem, right? That this system, so I'll call it A actually. Let's call this A instead of X, because X has other meanings, but A times X equals the 0 vector has only the trivial solution. So it has only the trivial solution, which remember means X equals 0, if and only if A is non-singular. So we can use our determinant to try to compute, right, whether or not A is singular or non-singular. Okay, so let's do this. Remember, you can change, well, let's just compute it, right? So let's use our method to compute the determinant of this A. So we should remember this theorem. But the determinant of A, remember the kind of calculational method that I have is to copy these columns and then multiply along diagonals here and subtract these ones, right? So just be careful how you draw them. And so the blue is going to be 0 plus 0 plus 0, right? And then the green is going to be minus 0 plus 0 plus 1. All right, and so altogether this is minus 1. Minus 1 is not 0. And so the coefficient matrix is non-singular, and therefore these vectors are linearly independent. All right? So the matrix A equals 1, 1, 1, 1, 1, 0, 1, 0, 0 is non-singular, and therefore its columns are linearly independent. This is the result here. So these are linearly independent. All right, so for the next example, I'd like you guys to try this one on your own, just kind of repeat what we just did. So this will be, once again, a set of 3 vectors in R3, but I want you to determine, so actually use the determinant method, but use the determinant to determine whether the following set of vectors is linearly independent in R3. So whether this set, so the set of vectors that I'd like you to check are the vectors 4, 2, 3, 2, 3, 1, and then the third one is 2, negative 5, 3. Notice that now it's not so clear to see whether or not these are, whether there's a linear combination of any of these or not. So use the determinant method to see if these are linearly independent or dependent. Okay, so guys, take a moment, work on that, and check back in when you're done. All right, now that you've had a moment to work on this one yourselves, let's try it together. So remember, the idea here is to write out the matrix. So the matrix A is going to be this matrix. It's like the coefficient matrix of the system, the corresponding system. And we then want to compute the determinant of this, right? So the determinant of A is going to be the number that we get by going through this whole process of computing the determinant. And remember, we have this kind of trick where we very carefully write out the other two columns and then add and subtract, right? And so our determinant here, I mean, this is kind of, I wrote equals. It's a little funky the way I've written it here, but we need to work this out. So this is just a computation, but this is going to be 4 times 3 times 3 plus, so I mean, we can just write this out. That's 24, right? We don't need to write out every single step, but this one's going to be, sorry, that's not 24. That's 36, right? So that one's going to be 36. Then this is going to be minus 30, and then plus 4. And then we're going to subtract off the rest of these. So this is going to be 12. Minus 20, and then plus 18. And then we just want to check and see whether we get 0 or not, right? So here we have 10 minus what's left in here is, this is going to be 30 minus 20. So that's also 10, right? And notice what happens. We get 0. So for this example, the determinant is 0. That means that the vectors, these columns, the columns of the matrix, are linearly dependent, but those columns of the matrix came from the original vectors in our set, right? And so our conclusion is here that therefore the set of those vectors 4, 2, 3, 2, 3, 1, and then 2, negative 5, 3, these are linearly dependent. Now at this point you could try to find the coefficients that make one of these a linear combination of the others if you wish, but you don't have to, right? Because the determinant method has shown us that these are linearly dependent. All right, and that means the system has the system of equations that we would have gotten if we wrote out all the details like in the previous steps, that system would have had a non-trivial solution to the homogeneous system. All right, so at this point we've seen a couple of examples of trying to compute these things. Now let's write a theorem. So this theorem, I'm going to leave the proof as a recommended exercise for you guys, but I want to state it here because it's important. So it says the following. So let's let the set of vectors here, v1, v2 through vn, let these be vectors in V. So I wrote it as a set, but what I mean here is that each individual vector is a vector in a vector space. Remember that we're working in generic vector spaces. So far our examples have been the vector spaces Rn, right, for the vertical vectors that we're used to from calculus class, but this is a generic vector space, V. The theorem then says a vector V in the span of these vectors. So remember, the span of our vectors always forms a vector space. So a span is always a vector subspace of the vector space, but if a vector V in the span can be written uniquely, that means there's only one way, right? Uniquely, as a linear combination. This is going to be very important moving forward. Linear combination of these vectors v1 through vn. This is going to be true. We're going to be able to do this if and only if these vectors are linearly independent. So v1, v2. And the uniqueness part is what really makes this important here. So if and only if these vectors are linearly independent. So it's always, if we have a span, right, then it's always going to be possible to write our vector as a linear combination of the vectors v1 through vn, because that's the definition of the span, right? The span is a set of all vectors v for which they can be written as a linear combination. So the key here is the uniqueness. So it can be written uniquely. So there's only one set of coefficients that gives us this vector v, if and only if these vectors that form the span are linearly independent to start with. Okay, so this proof is in your textbook. I'd like you guys to read through it and at least try to get the idea of what they're doing. We worked through a couple proofs together in this lecture, so I'm going to leave that one as an exercise for you guys. To end this lecture, we have a couple more things that we'd like to talk about, and they're closely related. So these are going to be related to the function spaces. So far, like I said earlier, we've only talked about vector spaces in this lecture, Rn, right? The vector space is Rn. And it turns out that in general we can do most of what we need to do in Rn, but that'll be for a future lecture. Actually, in the next lecture we'll talk about that a little bit, and then we'll really get into it after that. But we still do need to be able to work with the general vector spaces, and especially the function spaces. So let's look at this following example. So let's suppose that we have the following polynomials in P3. So let's consider these P1, P2, and P3, subscript 3, all in the vector space P3. So I guess it's also a subscript there. But remember, these are the polynomials of degree at most 2, right? 2, 1, or 0. So at most 2. But I'm going to actually give us vectors here. So P1 is going to be the polynomial whose formula is x squared minus 2x plus 3. P2 is going to be the polynomial 2x squared plus x plus 8. And P3 is going to be the polynomial x squared plus 8x plus 7. All right, and I want to know, are these linearly independent or not? So are these linearly independent or linearly dependent? So we'll say Li or Ld. All right, so there's our question. So what I'd like you guys to do is try to remember, before I leave you guys, I'll remind you, the 0 vector in this space, right? So recall, the 0 vector in P3 is the polynomial, right? The polynomial whose coefficients are all zeros. So using this fact, I'd like you guys to try to take a moment during the pause in pencil, to write out a system of equations to determine whether or not these 3 vectors are linearly independent or linearly dependent in P3. And then you can try to actually solve it if you want and answer the question. And then when you come back, we'll do it together. Alright guys, so remember we're trying to figure out if these 3 polynomial vectors are linearly independent or linearly dependent. So what we need to do is write out the system of equations. C1 P1 plus C2, so P1 of x if we wish, C2 P2 of x plus C3 P3 of x is supposed to equal the 0 polynomial, right? 0 of x. And then if we write this out, what we see is we get C1 times, write out our function, x squared minus 2x plus 3 plus C2 times 2x squared plus x plus 8 plus C3 times x squared plus 8x plus 7. And this should be equal to the 0 polynomial. So we can write this out as 0x squared plus 0x plus 0. And at this point, what we want to do is try to separate these by their coefficients, right? By the powers of x, I should say. So what I mean by that is if we look at the x squared terms on the left-hand side, the coefficients of those on the left have to add up to the same thing that is equal to on the right, which is a 0, right? So this needs to be, if we regroup this will be C1 plus 2C2 plus C3 times x squared plus, this is going to be negative 2C1 plus 1c2 plus 8c3 times x plus, then we see 3c1, right? And then we'll just write it this way. So plus 3c1 plus 8c2 plus 7c3, and that's got to be equal to 0x squared plus 0x plus 0. And so this is how we get our system of equations at this point, right? And so at this point we can see our equations are going to be c1 plus c2 plus 2c2 plus c3 equals 0. There's the coefficients on the x squared terms. The next terms, the x terms, they're going to be negative 2c1 plus c2 plus 8c3 equals 0. Homogeneous, right? It's always going to be 0 on the right-hand side. And then the third equation is going to be 3c1 plus 8c2 plus 7c3 equals 0. All right? This is our system, and so we can write this then as a matrix equation, where our matrix is negative, our coefficient matrix is negative, it's 1, negative 2, 3 in the first column, and then it's going to be 2, 1, 8 in the second column, and then 1, 8, 7 in the third column. C1, C2, C3, these are our unknowns, and it's homogeneous, so the 0 is on the right-hand side. So there's the matrix equation. Now, just scroll up a little bit and we can compare, right? Notice that the first column of this matrix is the coefficients here are the coefficients of this polynomial, right? The first polynomial. The second column, the coefficients are of this polynomial, and the third column, the coefficients are of this polynomial. And so at this point, what we have to do, or what we notice here, right, is that what we could have done, and you can do this in the future, right? You have to do it once on your own, but then what you can do in the future then is just notice that the columns of your coefficient matrix are the coefficients, if you put them in order, the coefficients of your polynomial functions here. Okay? So now we can do the same thing that we've done before, though, right? Because at this point we have a coefficient matrix. We want to know, is this singular or is it non-singular? So at this point we just want to compute the determinant and check that. That's the easiest way at this point. Now that we have that tool in our toolbox, that's the way to do it, right? So our matrix A is 1, negative 2, 3, 2, 1, 8 in the second column, 1, 8, 7 in the third column. All right? We're going to compute the determinant as we've done throughout this lecture, right? So that's a 1. Let me fix it because I'll probably misread that. All right, and then we can just, again, do our same method here of computing. Multiply these, add the blue, subtract the green, right? We're getting the hang of this. So this is going to be 7 plus, this is going to be 48, right? 7 plus 48, and then minus 16. And then we're going to subtract off all the green ones. So the green, this is going to be minus 28. This is going to be plus 64, 8 times 8, and then plus 3. And remember, we don't really care what the answer is other than that, whether or not it's 0, right? But we'll work it out. So this one's going to be 55 minus 16. So that's 39. Minus what's left here is going to be 67 minus 28. That's also going to be 39. And so look at, we got 0 here. And so that means that actually these polynomials are linearly dependent. All right? So these polynomials that we were given, we don't have to rewrite them, but these polynomials P1, P2, P3, these are linearly dependent. Okay? All right, so we have one more thing that we'd like to talk about, and it's very closely related to what we just did with these polynomial functions. So the question now is, how do we determine if a set of functions that are not polynomials are linearly independent or not? So if they're more complicated functions. And the key to this is something called the Wronskian. So this is item number 9 of our lecture. Again, this is called the Wronskian. And so here's the idea. We'll do the general setup and then we'll do an example or two. So let's suppose that we have, in this case, n functions, so f1, f2 through fn, in at least cn minus 1. So you have to have at least n minus 1 derivatives for continuous derivatives for these functions. So Cn minus 1 of AB. And we'll see why in a second. So again, we want to determine whether or not these are linearly independent or not. So let's start by supposing they are. So let's just write down the formula, right? So if we don't have to suppose that they are, but the equation that we want to solve, right? The linear combination is going to be the following. So let's consider the linear combination C1 F1 plus C2 F2. C2 F2. So C2 F2 all the way up through Cn F sub n, and that's supposed to equal the zero function, right? So what this means is that for any x value, any value of x that we plug into these functions between a and b, that this sum equals 0, right? Now, because these functions are differentiable and their derivatives are continuous, then if this sum is equal to 0, we can implicitly differentiate this entire equation. So we could take d by dx or d by dt, whatever the independent variable is, of this entire equation, and we find that, again, since the derivative is linear, and these c's are just constants, then taking the derivative, we end up with c1 f1 prime plus c2 f2 prime, etc., through cn fn prime has to be equal to 0 as well, right? Just by the linearity of the derivative. And we can then do this n minus 1 times. So we can repeat this until we end up with c1 f n minus 1 derivative plus f1, c2 f2 n minus first derivative, all the way through cn fn minus first derivative of fn. That should be equal to 0 as well. All right? And then we can just make a matrix equation of this, but it's like a formal matrix equation, right? So we obtain, in this sense, a formal matrix equation. Formal matrix equation, which looks like the following. So the matrix is going to be, the columns are going to be the functions and their derivatives, right? So f1 and then f1 prime, and then all the way through to f1, the n minus first derivative. Next column is going to be f2, f2 prime, all the way through to f2, n minus first derivative. And then it's going to go over to fn, fn prime, all the way down to fn, n minus first derivative, multiplied by the vector of the constants, and should equal 0, right? And so we've already seen now that when we write these matrix equations with the coefficient matrices, that we can check the determinant of these, and if the determinant is 0, then we get linear dependence. If it's not 0, we get independence, all right? Now, this is not necessarily going to be exactly the same, but the idea is going to be the same, and that is that we're going to want to take the determinant of this matrix. When you take the determinant of a matrix whose entries are functions, you end up with a function, right? So the function defined on this interval, so defined on the interval from a to b, and it's given by what we'll call, so if this matrix right here is called W with a hat, so I'll call this matrix W with a hat, then this is given by, the function is given by W, which in our book they do W brackets F1, F2 to Fn of x, right? So it's a function. This is just defined to be the determinant of this W hat of x. So you would either compute the determinant first and then plug in your x value, or you can plug in x first and then compute, and you'll get a value that way. Either way is fine. But this is called the Wronskian. So this is called the Wronskian of this set of functions. So f1, f2 through fn. All right, and with the Wronskian, we obtain this theorem. And so the theorem, it turns out, is only a one-way theorem. But the theorem says, let's let f1, f2 through fn be functions in this function space Cn minus 1 AB. Right? Exactly the same situation that we just built the Wronskian with. And here's what the theorem says. So if there exists a point x naught, we'll say, in the interval from a to b, for which the Wronskian w of f1, f2 through fn applied at this point x naught is not equal to 0, all right, then our functions are linearly independent. So then f1, f2 through fn are linearly independent. All right, so this is a one-way theorem though. So if the Wronskian is non-zero at any point in the interval, then that means that the functions are linearly independent. So let's see how this works with a couple of examples, or one example, I guess. We'll start with this one. Let's compute the Wronskian for cosh of x and sinh of x, so the two hyperbolic trig functions. So the basic trig functions, hyperbolic cosine, hyperbolic sine. All right, there's only two functions here, right? So that means that we only have to worry about the first derivative. These functions are actually infinitely differentiable, so we could take as many derivatives as we want, but we don't have to for this one. So our w, remember this is a function of x, so sometimes we write w hat as a function of x, but as a matrix, the first row is just the functions. This will just be 2 by 2 because there's only two of them, right? But there's our functions. And the next row is going to be our derivative. So the derivative of cosh is sinh, and the derivative of sinh is cosh, right? And so at this point, there's our matrix. That's not the Wronskian itself, but it's closely related, right? So there's our matrix, and then our function, our Wronskian function, which, if in context you know what these functions are, then you don't have to write everything every time, but we'll write it this time. This is going to be the determinant, right? The determinant of w hat of x. And therefore, we just do this, simple crisscross multiplication. So this one will be cosh squared of x minus sinh squared of x. And I'm sure you all remember your hyperbolic trigonometry, right? This is the Pythagorean theorem for hyperbolic geometry. Cosh squared minus sinh squared is equal to 1. Identically equal to 1. It's always 1. All right? And so it's actually equal to 1 for every x value, right? So based on our theorem up here, not only is it not 0 for some value of x, it's not 0 for every value of x, right? I didn't even give an interval here, so we can consider this to be on C1 of all real numbers, actually, right? But the point is that the Wronskian is not 0. The Wronskian is 1. So that means that these two functions, cosh and sinh, are linearly independent. All right, on either any interval or on R, all of R. But therefore, this is our set, right? Cosh of x and sinh of x. This set is linearly independent. Let's call it Li on C1 of R. All right, so there's one example. Now let's take a look at another example to end this lecture. This will be the last example that we look at. This is number 11 then. So number 11, let's look at the following functions. So these functions are x squared and x times the absolute value of x. So these two functions are going to be, we're going to look at these in the space C1 from -1 to 1. All right, so before we compute anything, let's look at the graphs of these things. So x squared, I think we all know what x squared looks like from -1 to 1. It looks like a parabola, right? It's our standard parabola. It goes right through the origin, so big point there. But there's our x squared. This is x, this is y. X times absolute value of x looks like when x is positive, it looks exactly like x squared. So they sit right on top of each other. But when x is negative, this gets flipped over, right? It's the reflection of this. And we're only looking at these functions from -1 to 1. All right, and so clearly they coincide on this side, but then they're different on this side of the x-axis, right? So they coincide exactly from 0 to 1, and then they differ over here from -1 to 0, or 0 to -1 if you go this direction. And the question becomes, so all right, are these functions, are they linearly independent or linearly dependent? So that becomes the question. Well, let's check. So we can try our Wronskian, right? So if we're going to try our Wronskian, by the way, we need to know the derivatives of these. So the derivative of x squared is just going to be 2x. We all know that one, right? The derivative of x times the absolute value of x is a little bit more complicated, and it's not that bad. But let's just first, before we write out the derivative, let's think about what this function equals as a piecewise function. So when x is positive, then this is just x times itself, right? So it's x squared when x is non-negative, actually. So when we see that from the graph, when x is negative, this one will become positive, and this one will keep its minus sign. So actually, when x is less than 0, we get a negative x squared, right? And so now we can think about the derivative as a piecewise function, if you wish. It's going to be the derivative of these terms, so it's going to be 2x and minus 2x, right? Again, when x is greater than or equal to 0, x is less than 0. And just based on this, we can say, all right, just looking at this, well, this is -2 times the normal absolute value function, right? So this is -2 absolute values of x. Okay, and so once we have these derivatives, then we can plug into the Wronskian. So the Wronskian of these functions, I'll just write w because we know what the functions are. So the Wronskian is going to be the determinant of the matrix, right? The matrix, whoops, I wrote this wrong. This is 2 absolute values of x. The negative sign is wrapped up in there, right? So I can't remember if I said it correctly, but it's just 2 times the absolute value. All right, now, as we now go to our Wronskian, the derivative of x squared is 2x. The derivative of x absolute value of x is 2 absolute values of x. And then we compute the determinant. So this will be 2 absolute value of x times x squared minus 2 x squared absolute value of x. Same thing, right? And so this is identically 0. Even on the negative portion, from -1 to 1, this is going to be 0, right? So this is 0 at all points. Now, does that mean they're linearly independent? Well, that's where the fact that this is a one-way theorem comes back into play. This just says if there exists a point for which the Wronskian is non-zero, then the functions are linearly independent, right? It doesn't say what happens if the Wronskian is identically 0. And when we go down and we look at this, well, that means that this is inconclusive, right? Inconclusive. If we get just 0, then our Wronskian test is inconclusive. And that means that we actually have to work this out, right? So we actually have to go back to our definition, which says that C1 x squared plus C2 times x absolute value of x should equal 0 at all points, right? At all points in this interval from -1 to 1. Okay? And we need to try to find the C1 and C2 that make this equation satisfied. So, well, first of all, this has to be true at all points in this interval, specifically at the two endpoints, right? So for x equal to -1, we can just plug in. This one says, okay, -1 squared is 1, so C1 plus, this is going to be -1. So it's actually C1 minus C2 should equal 0. And then in this case, the second case, right, if we plug in the other endpoint, x equals 1, this will say C1 plus C2 should equal to 0. All right. And so from here we can see, all right, C1 has to equal C2 from this equation. And when we plug that into this equation, we get 2C2 equal to 0. So C2 has to be 0, which then, of course, means up here, C1 also has to be 0. So actually, by the definition of linear independence, these two functions are linearly independent. But the Wronskian did not help us determine that, right? It didn't tell us that. So actually here, what we learn from just using the definition is that these two functions are linearly independent. All right, now that doesn't mean that it's wrong to try the Wronskian first, because in general, the Wronskian is a good tool to check this, right? It's a good tool to check whether or not your functions are linearly independent. If the Wronskian's inconclusive, though, then you have to go back to the definition. So that's what we should take away from this example. All right, guys, let's leave this one here, and I'll talk to you guys in the next lecture.